Most people look at a modern electric vehicle and see a traditional car that carries a battery. But the engineering reality is the reverse. An EV is a giant battery that happens to have wheels. First-generation EV construction relied on the cell-to-module, or CTM architecture. This is a method where individual battery cells are grouped together into standardized, swappable blocks called modules. This approach creates significant structural redundancy. Individual battery cells are placed into heavy steel modules. Those modules are then packed into an external, thick protective housing, which is finally bolted to the bottom of the vehicle's chassis. Because of these protective layers, the active chemical material that actually powers the car takes up less than half the total volume of the battery pack. The space utilization sits at 40%. The vehicle carries hundreds of pounds of dead weight in packaging alone, which cuts directly into driving range and forces designers to build taller, bulkier vehicles to accommodate the bloated floor pan. To solve this, the industry is moving away from the cell-to-module standard. Manufacturers are adopting third-generation integration systems, known as CTP, CTC, and CTB, to change the physical geometry of the vehicle. Simply inventing denser battery chemistries cannot overcome the physics of poor packaging. Maximizing the true potential of a modern electric vehicle requires a total architectural erasure of the battery pack itself. The first evolutionary step in this integration is cell-to-pack, or CTP. In this second generation of EV architecture, manufacturers like CATL and BYD eliminated the standard VDA module layer entirely. The VDA module is a standardized battery enclosure originally defined by the German Association of the Automotive Industry to ensure component cross-compatibility. Instead of those boxes, BYD introduced the blade battery array. Square internal modules dissolve, and long blade-like cells slide directly into the main pack housing, filling empty geometric gaps. This creates a significant jump in volumetric efficiency and higher energy density within the same footprint. However, cell-to-pack still has a lingering limitation. The battery remains a distinct, isolated component that must be bolted onto the bottom of the car during assembly. CTP successfully optimizes the box, but it fails to optimize the car around that box. Erasing the boundary between the battery and the vehicle requires the next leap in integration. That leap is cell-to-body architecture, or CTB. The current implementation of this is found in vehicles like the BYD Seal. In a CTB design, the body floor panel of the car and the upper shell of the battery pack are fused into a single flat sealing surface. This design forces the battery to act as a structural member. It actively participates in the vehicle's force transmission, taking kinetic force from a side collision and distributing it directly through the battery cell array itself. By turning energy storage into a load-bearing structure, this integration yields a 45% reduction in side pillar intrusion. The passenger cockpit is then sealed directly to this new battery floor combination, using specialized industrial sealants, eliminating redundant metal. With CTB, the battery transitions from being a passive passenger in the floor pan to serving as the load-bearing skeleton of the vehicle. The final architectural ideal is cell-to-chassis, or CTC, an approach currently pioneered by automakers like Tesla and Leapmotor. In a true CTC configuration, the external battery housing is deleted. Individual cells connect directly into cavities between front and rear giant castings. This delivers high-efficiency metrics. Matching efficiency pushes past 90%, space utilization breaks 70%, and components drop to roughly 400. But this level of integration entirely removes component modularity. While earlier CTP designs allowed for physical battery swapping stations, CTC and CTB structures cannot be quickly removed. This mandates an absolute reliance on fast charging infrastructure. Furthermore, eliminating the protective module layers creates critical thermal management vulnerabilities. The cells are packed tighter than ever, generating dense heat loads. Because of these thermal demands, heat pump air conditioning has shifted from an optional feature to a mandatory standard configuration to keep the integrated chassis within safe operating temperatures. Maintenance is equally strict. Traditional cell-level visual inspection is impossible. Any floor pan repair now requires precise high-voltage cutoff methods and advanced personal protective equipment, or PPE, just to safely access the structure. Repairability. The modern EV has become a singular, monolithic, and largely sealed unit. Beyond mechanical engineering, the transition to CTC creates significant ramifications for the automotive supply chain. Historically, battery companies acted as Tier 1 suppliers. They delivered independent CTP packs to automakers, staying entirely out of the automaker's core territory of chassis design and vehicle dynamics. CTC dissolves this boundary. Because the battery is the chassis, battery makers must now design the chassis itself to sell their cells. Battery giants like Cattle are aggressively expanding into intelligent CTC integration, absorbing power components like motors, electronic controls, and intelligent power domains directly into their own battery platforms. An intelligent power domain is a centralized computing unit that manages energy distribution across the vehicle. This creates an existential risk for traditional automakers. If they rely on a supplier for a fully integrated CTC platform, they lose control over the most expensive component of their own vehicles. Tier 1 battery suppliers have moved beyond building energy containers. They are now manufacturing the structural foundation of the car. To defend their territory, legacy automakers are developing their own highly integrated open-source skateboard architectures before battery makers can corner the market. Automakers are spending heavily to keep this capability in-house. Geely, for example, invested $2.5 billion into the Sustainable Experience Architecture, or SEA, and the GEA platform, a global intelligent new energy architecture that combines hardware, software, and AI systems into a single chassis foundation. CEA provides immense global bandwidth, acting as a foundation for everything from compact cars to SUVs. Furthermore, GEA integrates hardware, systems, ecology, and AI directly into the chassis, ensuring automakers retain control over the vehicle's brain and body. The transition from CTM to CTC represents the consolidation of the modern automotive assembly. The electric vehicle has evolved into a singular unit, where the power source and the chassis are integrated into a single assembly. The battery is the machine, and whoever controls the structural integration of the cell will control the future of global automotive manufacturing.